Thank you, Nils. And now Professor Tors Hans Hansson will give us some insights into the discoveries that led to the Nobel Prize. Hans, please.
So I'm very happy to be here and to tell you about this very deep and actually very beautiful work that is at the basis for this year's prize. And I will start by explaining to you a concept from the citation that might not be familiar to you, and that's the concept of topology. So I brought my lunch, and here you see, it's a cinnamon bun. Here I have another thing. I have a bagel, okay? And here I have a pretzel. It's a Swedish pretzel with 2 holes in it. Now, for us, you know, these things are very different. This is sweet, this is perhaps salty, different shapes, etc. But if you are a topologist, it's only one thing that is really interesting with these things in which they differ. This thing has no hole. The bagel has 1 hole. The pretzel has 2 holes. The number of holes is what the topologist would call a topological invariant. And just as you cannot have a half a hole or 2 2/3 holes, you can, for a topological invariant, only have integer numbers, okay? Only integers. And another thing which is very important for the following with topological invariance is that it takes something to change the topological number. I take this thing, you see, I can bend it a little bit, compress it, but in order to make it to change number of holes, I have to do something drastic. I have to break it apart. And this stability of the topological invariance is going to be important. So what does this have to do with physics? Well, if we go back to 1980, it was a beautiful discovery made by Klaus von Klitzing. He gave him a Nobel Prize in 1985, actually, for what's called the quantum Hall effect. What he did was that he took electrons, he confined them into thin layer at very low temperature and at extremely high magnetic field. And what he found was very amazing. He found that when he measured the electric conductance in this system, he could see it came in steps. Nothing, or 1 unit, or 2 units. And this unit that he measured was to an extreme precision. Sort of unexpected, because in these experiments you cannot control temperature and all other things very carefully. So why could you get something which is so precise? There were ideas about that, but the real breakthrough came with the discovery of one of today's laureates, David Thouless, who could show that these steps here actually can be explained as such a topological invariant. It's not exactly as the number of holes in a bagel or a pretzel, but it's something very, very similar. And this also explains why it is so precise, why it's so robust, why you get integer steps. And later on, 1988, Duncan Haldane, another of today's laureates, showed that you could do the same without having this very strong magnetic field. And for the continuation of this field, that was very, very important. Now, let's move on to the next concept in this citation, namely topological states of matter. Now, what is a state of matter? Well, this is something that you presumably know from school. If high temperature, you can have a gas. Lower the temperature, you get a liquid. Lower more, you get a solid. But when you lower temperature even more, close to absolute zero, there are new fascinating phases of matter. And the ones we talked about before, these electrons in a layer, that's such a topological phase of matter that you find at very low temperature. Now, this is not the only one. Haldane, in 1983, looked at another kind of system, a set of magnetic atoms in a chain. And he could show that even in this case, you had such an exotic topological phase of matter. And now, actually the race is on, and you look for topological phases of matter in chains, in layers, but also in ordinary three-dimensional materials. So that was two things. It was topology, it was states of matter. Now we come to the third, phase transitions. What's a phase transition? Well, how do you go from a gas to a liquid to a solid? You do it, you lower the temperature. Now, what is it that really happens? And this physicists have studied for a long time, and it was a good idea about how this transition occurs. And in particular, people believed that if you had these very thin layers, for instance, a thin liquid layer of helium, you would never have such a phase transition. That had been proven mathematically. But when people prove that something cannot happen, it might be that they haven't thought of everything. And the thing that they did not think of in this case was this thing. They did not think of, well, not tornadoes, but vortices. A tornado is like a big vortex. And it's topological in the sense you can have one tornado. If you're unlucky, you have two perhaps. But you cannot have half a tornado. It's topological in the same way as the number of holes. That's a big one. Here is a small one. This is the artists rendering some layers of liquid helium. And you see there are small vortices here. Here we have a blow up. You can see the liquid is whirling around here. Now, at very low temperature, these vortices always comes in pairs. Actually, it's one vortex going in this direction and another one going in that direction. It's a pair of vortex and anti-vortex. They keep together. When you raise the temperature a little bit, then what happens is that these super tight pairs, now they will sail away and they become free. And that is a phase transition, a completely new kind of phase transition driven by topological effects. And this was also something that you could apply in many places, and the basic paper was written by Kosterlitz and Thouless, who found the phase transition and understood the vortex mechanism. And in a later paper by Michael Kosterlitz, he also worked out the detailed mathematical theory. And this is something that applies not only to helium films, but to lots of systems, and it's been very important for the following. Now, that was very shortly what it's about. Now, I will answer the question that you are going to ask, namely, what's it good for? Because I know you're going to ask that. But before I answer that question, let me tell you something that I feel deeply about, the committee feels deeply about, I think all people in physics feel deeply about. And that is that this prize here is for theoretical discoveries. It has combined beautiful mathematical and profound physics insights and achieved unexpected results that has been confirmed by experiments. That's what the prize is for. It's really beautiful and it's deep. Having said that, this work has inspired lots of activity in labs all over the world, international research. Scientists are hoping for practical applications in new electronics, new materials, even perhaps components in the future quantum computer. It has opened this field. It's very exciting, but the prize today is for this. Thank you.
Thank you, Hans.